My name is Marina Phillip. I'm an educator at Explora, and we are here to share with you some activities that are related to renewable energy and sort of a scaffold, a great way of introducing the technology behind many renewable energy resources to your classrooms or to your basic groups. One amazing thing that we have to hear today is our collaborators at Sandia National Labs, who a group of interns last summer developed these activities with me, and Elaine is here to share with all of us an introduction to marine energy, sort of the centering concept that we sort of built a lot of these activities around. So,
Yeah, so hi everyone. I'm so excited to present to you guys a little bit of brief overview of renewable energy and specifically marine energy. And I'd like to start off by introducing myself. I'm Elaine. I'm a second-year master's student studying mechanical engineering at Stanford, and I've always been interested in marine applications of engineering. I did my undergrad at Northwestern, where I was involved with building underwater robots to help compete in a collegiate competition and accomplish tasks. And in my classes, I also work on developing remote control boats, just for the fun of like shooting water into other people's boats. And in my free time, I enjoy paragliding at San Diego and just traveling and experiencing new things. So yeah, with that, I'd like to bring you guys to the agenda for today. I'd like to start off with an introduction to Sandia, our core mission and our values, and then transition into how that informs our research into renewable energy and how it impacts our U.S. clean energy goals and what exactly that is. Then we'll talk about the more specifics of the current state-of-the-art technology in marine energy, as well as the different ways that we can harness electricity from the ocean and the different types of devices associated with that. Then I'll conclude with a summary and opportunities on how to get involved as well as educational resources. So Sandia's history is actually traced back to World War II during the Manhattan Project to develop the first atomic bomb. Sandia started out as a division under Los Alamos Lab to design and test the non-nuclear components of the nuclear weapon. It has sort of advanced this core mission to protect the national security interests and also mitigate any threats or internationally as well. Throughout the years, it's been managed by different corporations, but in 1949 it was established as its own entity. So Sandia has still retained its core mission to protect national security interests, but has expanded its role onto other areas of research interest, such as renewable energy studies and climate analysis in light of the warming temperatures and climate change, which is a national threat. It also has expertise in mitigating the other national threats and improving our resilience of national infrastructure such as the electrical grid. With that, we'll talk more about specifics of renewable energy. So what is renewable energy? Renewable energy is energy that we can harvest from naturally occurring resources, such as the sun's solar rays, or wind, and the natural oscillating motion of the waves and currents from the ocean. This means that we can use naturally occurring resources that are continuously replenishable, which is in contrast to mining for fossil fuels. And that means that the key attractive trait to renewable energy is its reduction in carbon emissions. So it's clean energy and doesn't require, burning for fossil fuels that would emit air pollutants. And because this energy is abundant, free, and naturally occurring, it means that we have strengthened energy security and independence from our reliance on fossil fuels and other nations that would contribute to the negative effects of climate change. And this renewable energy is super important to helping us meet the U.S. clean energy goals. Our nation has set these timelines and metrics that we need to meet to help mitigate the effects of climate change such as cutting carbon emissions by 2030, reaching 100% clean electricity by 2035, net zero by 2050, which means that we need to develop a cost-effective solution to help us contribute to this clean electricity supply. At Sandia, we work on 3 core values for these renewable energy research. We want to reduce the cost, improve the resilience, and improve the reliability of such a device. We work on anything ranging from the more mature solar and wind technology to help improve its power performance and reduce its cost and improve its reliability, but also more broader areas of renewable energy and different types of energies, such as geothermal, which uses the energy from the Earth's core to power generators and generate clean electricity, or bioenergy, which involves synthesizing next generation fuels for our automobiles and other uses. Sandia is also involved with the water power program, which is designed to harness energy from the ocean's waves, which is the department that me and Kelly are in, and we're going to talk more about that later. So I mentioned that solar and wind are more mature technologies, and that we have this sort of breadth of research and development into different areas of renewable energy. But why would we want to focus specifically on marine energy? Well, actually, it turns out that our portfolio of energy right now is, like each renewable energy contributes a different advantage and benefit to our energy supply. And we need to diversify and bring in these different advantages that different renewable energies bring. So marine energy in particular is extremely predictable and reliable. The waves are continuously occurring, which is in contrast to solar and wind that depend on when the sun is shining or when the wind is blowing. But we know that the waves are always going to be oscillating and producing this energy. It is also in high proximity to high density populations. Most of the, globally, most of the population lives around bodies of water or the ocean. In the US, the majority of the population lives around West Coast or East Coast, which means that marine energy has a high potential to power these populations because it's in high proximity to it and would reduce some of the transmission costs that's associated with long distance transmission of energy. It can also complement solar and wind because it does have this continuous base level of generation as an energy source, and can also help us meet energy demands in the ocean, such as from oceanographic buoys, aquaculture farms, anything that requires electricity, marine energy can contribute to. This is a chart showing us just how much marine energy resource we have in the United States. It has been calculated that we have up to around 800 terawatt hours a year of power, which is equivalent to powering 20% of the total electricity generated by the United States in 2019. We can bump that number to be even higher, to be 57% if we incorporate Alaska and Hawaii. This means that this is a tremendous untapped potential to help us contribute to our clean energy goals. But with that being said, there are significant challenges with marine energy that lead to the device not being deployed as much. The device is in a harsh marine environment, so due to extreme winds, waves, storms, that makes it very difficult to engineer a reliable device. It also, because of that, it also experiences high capital and operational and maintenance costs, which make it even harder to deploy a device. There are also significant ecological and environmental concerns that you need to go through a hurdle to deploy such a device. There's a lot of costly and lengthy permitting process in order to establish that your device doesn't endanger any marine habitats. And lastly, this is still an emerging market, which means that there hasn't been a convergence on a technological archetype, or there hasn't been a universal agreement into a particular device that is known to reliably and consistently generate electricity. Sandia is using our research and engineering expertise to help us mitigate some of these challenges and contribute to the advancement of the marine and energy industry. We contribute all aspects to the device, such as the materials and coding, the code development, controls, as well as some oriented for the public policy side, such as resource characterization, environmental analysis, and how we can use that to help power some of our blue economy needs in the ocean, such as fisheries. With that, we can transition into more specifics on marine energy, how we would actually harness this energy and what those devices look like. So the three main types of energy that we can harness from the ocean involves the waves, tides, and the currents in the ocean. So wave technology uses the oscillating motion of the waves in the middle of the ocean that occur due to the moon or the wind blowing over the surface of the waves in order to generate electricity. Tides generally use differences in elevation of high and low tides and use that difference in potential energy to drive turbines or power generators to generate clean electricity. Currents are smaller scale devices and they generally use the underwater flow of current of ocean to push through turbines that generate electricity. Ocean thermal uses the differences in temperatures occurring in an ocean, such as the hotter surface temperatures in contrast with the cooler bottom surface temperatures would power this thermal cycle that can be used to generate electricity. Salinity gradient uses the differences in salt between freshwater and saltwater concentration, and we can actually harvest that chemical difference to drive clean electricity as well. But what do these devices look like? So we have four main types of devices, or the most common ones that we can use to harvest electricity, and we'll talk about what those look like in the later slides. We have point absorber, attenuator, oscillating water column, and overtopping devices. So these are just kind of what the devices look like as to how we would actually harness the energy. As you can see, there's different shapes, configurations, sizes, and different mechanisms that we can harvest the energy with. So that just goes to show that marine energy is still an emerging market, and there hasn't been an agreement as to one particular device that we can use. With that, we'll talk about what each of these look like. So a point absorber is a device that usually consists of a floater that relies on relative motion to harvest energy. So as the waves oscillate, bobbing up and down, the floater bobs up and down, and there's a mechanism inside that is either compressed or decompressed to generate electricity. So some of these pictures highlight, the one on the right, highlight this fully submerged vertical tube that contains a piston. So as the floater bobs up and down, the piston is compressed and decompressed to drive electricity. There's also different orientations that we can harvest this relative motion of. As seen in the yellow top left picture, this one uses a sliding mass and is sort of rotating in this left and right pitching motion, and that resistance to the sliding of the mass extracts power and generates electricity. Next, we have attenuators, which are similar to the point absorber, but instead use a different orientation. So these are parallel to the waves and instead sort of ride them. They are consistent with these multiple steel segments that are these joints in this type of device, and as the waves are oscillating underneath them, the segments bend and flex, and that relative motion is captured to generate electricity. This type of device is already being deployed as part of a wind farm in Portugal and can generate up to 2.25 megawatts of power. Then we have oscillating water columns, different than the previous devices in its size. So it's much bigger than the smaller point absorber that are just floaters. They use giant chambers, and the water is oscillating inside these chambers and sort of pushes air at the top of the chamber. And when you have water oscillating underneath it, it compresses the air at the top and forces the air through a turbine. That's how energy is generated. So these are more larger scale and involve the use of a turbine. Similarly, we have overtopping devices, which also involve the use of a chamber and turbine, but instead use the waves themselves to crash onto the turbine, making it spin and generating electricity. So there's a couple of clever designs that people have come up with in order to focus the waves inside their basin and to spin the turbines. The Wave Dragon employs these use of wave reflectors that focuses the waves inside of their chamber and use the potential energy and momentum of the waves crashing down to spin the turbine. There's also a design called the tap chan, which is short for tapered channel. And so there's a collector to collect the water inside of a basin, and the excess water goes through a turbine and back into the ocean in this sort of cycle. The collector is also cleverly carved into a cliff, and it uses natural resources to collect the water inside their basin and drive through the turbine. So that kind of just concludes our summary of the devices and the types of energy that we can use to harvest. We talked about how we need a diverse energy portfolio to meet our U.S. clean energy demands. Different types of renewable energies will contribute different advantages, which means that we need a diverse portfolio to bring in all the advantages together. Marine energy is different than the others in that it's more predictable and consistent, because we have a lot of research and studies into where the ocean waves are strongest and when the tides will occur. Marine energy is also located near population centers, as it's near the coastline. A lot of residents live there, which means that it can power a majority of the local population. We also discussed different types of energies that we can harvest from the ocean that involve the waves, the tides, the currents, and different devices associated with harvesting each respective wave we can harvest from the energy. And then marine energy is also an emerging market, which means that it has a lot of potential to grow and contribute to our diverse energy portfolio. We also have a couple of slides on the opportunities and educational resources that you can check out. So primary is an educational resource that contains an abundant information on the current state-of-the-art marine energy industry. It contains a lot of information on the open source software and code that developers use to inform themselves with the wave conditions, and a lot of a summary of a more comprehensive summary on the different devices available. We also have, for more younger audiences, Techies, which is like an educational resource for young kids to understand marine renewable energy, and this reframes our message into one that more focuses on climate change and it's the marine environmental effects of deploying such a device.
Does anyone have any questions for Elaine?
Yeah.
So how is the transmission of the harvest then? Like, are we laying wires, are we digging, how are we, is it battery with pickup? Like, how do we not destroy the marine ecosystems with obstacles or big digging?
So it sometimes depends on the application. So currently I'm working on this wave energy device that can power oceanographic buoys, and that serves to recharge a battery and help its sensors be functional. Different applications for the grid scale can include digging under the seabed and having cables that route through from the ocean into inland.
That's pretty disruptive though to the ecosystem.
Yeah.
But it would be interesting to think about harvesting by leveraging our fisheries. Like fishery boats could be engaged to pick up battery packs and deploy out new batteries as part of their fishery services in a partnership of we're trying to have renewable energy. You guys are working with depleting resources as well. Here's a side gig that can help you with your hustle.
Yeah, there's definitely a lot of applications for this sort of mutually beneficial application. Like you mentioned fishery, there's a lot of studies being looked into for using wave energy to power current aquaculture farms, desalination plants, or to help synergize with offshore wind.
That's going to be pretty disruptive to some pretty fragile coastal marine ecosystems that already take a lot of traffic and a lot of damage. I have one other question, if you'll indulge, and that is, how do we make sure that when we are harvesting from things like ocean currents that are heavily used by marine organisms that use them for transportation, how do we not turn our energy harvest into a marine ecosystem energy deficit
Right.
for migrating organisms, for organisms that use those coastal currents, that use those ocean currents to go through their life cycle. Kind of like we saw with the birds with the wind turbines, like, oh, this is the best spot with the best wind, and then it's like a migratory corridor. Because the natural world has already identified those places, and those organisms are already using them as part of their survival to not energy deplete so that they don't starve to death along their way.
Yeah.
So, like, how do we balance our need for renewables against the natural world's already intuitive, innate, instinctual use of those same resources?
Yeah, that's definitely a good point. I know that there's been a lot of research into ways that we can mitigate our environmental effects of deploying like these current devices. So people have been designing these fish-friendly turbine blades where it sort of like curves and just kind of lets the fish pass through, or like fish ladders where we don't affect the migration patterns of such fish by just letting them sort of route through the turbines. Yeah, and that's also like one of the challenges that this industry is facing, where it's just difficult to deploy and justify that there would be no environmental impacts.
Yeah, and if you don't mind, I can chime in as well. So I'm Kelly Brule, I work at Sandia National Labs, I support the water power program. So for the first question, in terms of, so the first one was more related to like powering the blue economy market. So Department of Energy funds this whole initiative. It's called Powering the Blue Economy, and it's looking for those synergies between renewable generation and different ocean uses. So the program that Ali was talking about, that's an ocean observation related program. So right now for ocean observation, we have all kinds of instrumentation all over the world that are collecting meteorological data, oceanographic data. Right
Who's
now,
already out there?
those are all battery powered, and those batteries, they expire, they have to be replaced. You're sending vessels out all over the world to do that, and so different renewables, often solar and wind, right, are viable options. In some locations, those are not great options. So, like the project that Wade was talking about, there's opportunities to leverage wave energy in a synergistic way to support efforts that we already have ongoing. So like aquaculture, things like that. That's the whole focus of the Powering the Blue Economy initiative. Is like, how can we use the ocean resource to power things that we already have in the ocean that need power, that it's right there. In terms of the transmission to shore, for utility scale power generation, that's the option, right? It's going to be a subsea cable to shore. There are companies. There's a company that just came out that's actually looking at hydrogen storage. So they're actually planning on collecting hydrogen and then bringing it to shore. And their vision is to use like an electronic ship to it. So there's a lot of different frameworks in terms of how that energy could be harvested and used. And on the other question, in terms of environmental effects, that's an area that Sandia works in extensively. And part of the environmental permitting process for any of these types of projects, including offshore wind or any other, is you have to do an environmental impact assessment. And part of that environmental impact assessment is what are some of the, do you have a whale migration path? What are the species in that region? What are the potential impacts? And you have to either demonstrate that there's no impact, or they have these things called continuing monitoring plans, where they have to establish a baseline. And then throughout the project's life, for a certain period in that environmental impact assessment, it'll specify how long they need to go out and do continued monitoring and compare if there is an impact, they need to make a change. Elaine gave a great example for like the fish with turbine blades. Of course, that's a consideration. I do want to point out that these turbines are not, it's not like going fast, like they're spinning slowly, so but there's still potential for collision. So there's a deployment right now, a tidal deployment, where they actually have sensors, right, where if they see any sort of large animal coming through, it'll actually stop the turbine. So those are things that are being addressed, and that's a lot of the research that Sandia does in this space.
I know there's been some interesting around rollers and things to make bubble curtains that disrupt sonar as an obstacle so that the oil can go around.
Yeah,
Like there are some clever ways to get around, but if we're looking at large scale hydroelectric, marine hydroelectric, that brings a lot of issues.
Sure, certainly.
Sorry to derail.
No, there's that balance, right? And that, and that's an area that Sandia actively works in, is, I think on the slide you showed, right, it talks about, environmental effects, those are the types of things that we study. We have numerical models where we extract energy out, and we try to understand, okay, what's the real impact of the resource? Like for wind, you see that there's a localized wake, and then the wind regenerates within, it's like 5 to 10 rotor diameters downstream. You see that the wake is like fully recovered, and that the flow is fully recovered. And I think in turbines, it's similar. So it's like, yeah, you might be having a very localized extraction of the current, but
Because the wind as a whole regenerates quickly back.
yeah, and we have numerical methods to be able to evaluate